Hello everybody, how are you? This is a video to help you interpret regression output. The output that we're looking at right now is the same output that we looked at on the exam, and I just ask you to interpret what you're looking at. The very first thing you should look at is this significance F p-value. That's this quantity right here. That's a highly negative number. It's 7.3 to the negative 15, right? We're looking for approximately 0.05 significance there. Some people, if you wanted to be really certain about your model, you look for a lower number such as 0.01 or better. But this is really a highly significant model, and if it wasn't significant, there's really no point in going any further with any other analysis. Okay, but the fact that it is significant means we can go a little bit farther. Next thing I would look at is the R-square value, or the adjusted R-square value. These are pretty similar. Let's just think about the R-square. This is the percent of variance that is explained by the model. Okay, so this particular model is forecasting sales of RV units, and it's using several different variables to predict that, such as how much TV advertising did we spend, how much newspaper advertising, what's the price of gas, things like that. Generally speaking, you want a higher R-square value, but what I'm really looking for here is a point that I tried to make many times in class, and that is, to determine if 0.59 is good or bad, you really have no idea unless you have something to compare it to. Some models, if it's something that's a very difficult thing to forecast, if you get an R-square of 0.05, it could be good. There are other models of things that are very easy to forecast, in which case you might have an R-squared of 0.9, which is very bad. So when I look at that 0.59 right there, that really doesn't really mean much to me unless I have something relative that I can compare it to. Okay. If I'm looking at two different regression models, maybe I have a different regression model that forecasts RV sales, and if they're both significant, now maybe I'm going to look at R-squared in order to compare the two values, right? So one value, this one gives me a 0.59, maybe the other one gives me a 0.39, in which case this particular model we're looking at gives us more explanatory information, or it helps us predict a little bit more reliably. The next thing that you should look at is the p-value quantities of the coefficients. Okay, we're looking first of all, the intercept. This is the y-intercept. The significance of that doesn't really matter. Okay, so you can ignore this. It still needs to be in there, but you can ignore it. But these other p-values, we need to have, let's shoot for less than 0.05. Okay, so that means that newspaper is okay, that means that gasoline is okay, that means that list price is okay, and promo is okay. However, TV advertising has a high p-value, so this model should be rerun without TV in the model. Should just take it out of the data set and rerun it. Okay, and when we do that, it will give us a better look at the relative impact of the other coefficients, newspaper, gasoline, etc. Okay? The next thing you should look at, let me delete my marks. The next thing you should look at is what I've been calling the reasonableness of the coefficients. And reasonableness can be measured a couple of ways. One, you should look at the sign of the coefficients and just see if it looks like it's going the right direction. For example, newspaper advertising, this coefficient is positive, and that makes sense, right? The more we spend on newspaper advertising, the more RV units we sell. Okay, if we were to see something that didn't look reasonable, let's say, for example, the gasoline, if this gasoline coefficient was positive, then that would mean as gas prices go up, RV sales go up, and that's not reasonable. Okay? So looking at the sign is the first measure of reasonableness. The second measure of reasonableness is magnitude of the coefficients. Insert an A in there. Magnitude. I like my mouse writing. Magnitude. So that means we need to look at the size of these coefficients. Okay. If this was your data and you were very close, let's say it was your job to predict RV sales, the size of these coefficients may make a bigger difference to you. For example, if the price of gasoline goes up by $1, we sell 81 fewer RVs. That's what this coefficient is saying. If this is your business, you may know if that is a reasonable amount or a not reasonable amount. You and I probably don't have any idea right now, but whenever you interpret it, you have to look at the size of those coefficients or the magnitudes of them to decide if they are realistic. Okay? Another thing that you should pull out of this analysis is the high correlation of gasoline and people, right? It's 0.9. A high correlation is, let's say, 0.8 and above, just to give you a general guideline. The high correlation between people and gasoline means that these two coefficients, this coefficient, what's the other one? People. People, average number of salespeople on the lot during operating hours. That actually didn't make it into the final model, okay? Probably because it's highly collinear with gasoline advertising. When you have two variables that are highly collinear, you can't distinguish between the impact that they each make, okay? This is that example that I used in class was the amount, if you were trying to use the amount of scotch and beer and wine to predict your blood alcohol level, you could predict your blood alcohol accurately by counting the number of glasses of wine, scotch, and beer that you had. However, you wouldn't be able to tell the impact of each one. In other words, all the coefficients together would help you add up and predict a good blood alcohol level. However, the coefficients would not be reliable, okay, because they're all doing the same thing. So that's what we have in this model. We have a collinear relationship between people and gasoline advertising. So if you want to have good and reliable coefficient numbers, then you have to remove one of those items from the data set. The next thing that you would interpret from this information is you could predict RV sales. Okay, now you would have to know how much money you spend on newspaper advertising, and you'd have to know the price of gas. But you should, if you were given that information, you should be able to plug that into an equation and calculate RV sales. Okay. Those are the principal, most important things. I'll mention one more. Okay, one more. Up here at the top, this model forecasts RV sales in Boca Raton, Florida. Okay, we mentioned this in class. Now, what happened is, to run this model, we collected a bunch of history on RV sales in that particular area of Florida. Um, Regression models are only able to predict within the environment where the data was collected from. Okay? In other words, if I wanted to use this model to predict RV sales in Wichita, Kansas, I would not be able to do that reliably because this model was built for Boca Raton, Florida. It was using Boca Raton information, and although it may be similar to the sales in Wichita, Kansas, it cannot be reliably used. This model cannot be counted on to give you true information in another city. One particular example that you should all be able to relate to is just the price of gas, right? The people in Boca Raton, Florida are wealthier than the people in Wichita, Kansas. Therefore, the people in Boca Raton may be less sensitive to the price of gas than they are in Wichita, Kansas, okay? And there could be a number of other things going on that you don't realize. You know, the important thing to keep in mind is a model can only be used for the range of data that it was used to collect. Okay, another similar thought to that. Similar. Okay, let's say that we collected information from RV lots in Boca Raton, Florida, and one of those variables right here. Where's my mouse? People, right? The average number of salespeople on the lot during operating hours. Okay, if in our example we had days where we had one salespeople on the lot during operating hours, and other days we had, let's say, 5 salespeople during operating hours. That is, in effect, a range of applicability of the model. In other words, if we wanted to see what would happen if we had 10 salespeople on the lot, this model could not be used to do that because it wasn't built with data when 10 people were on the lot. Okay, so it's very important that these models be used only where they've been intended to be used, right? And in which case it can't be applied other ways. Okay. A few more things that I want to mention at this point. We mentioned them in class. You weren't really tested on these at this point. However, they are important whenever you want to use a model like this. And they're related to the data. So let's say that to build this model, we collected, I don't know, 400 days of RV sales, right? Every day of each one of those 400 days, we calculated the price of gas, and we calculated how many salespeople we had on the lot and how much TV advertising we did. So we had 400 observations to build this model. You need to look for outliers. Before you run this regression model, you need to look at all of those and see if the data points look reasonable. Okay? For example, the price of gas. Maybe you're looking down through all those prices of gas, and every day they're $3.30, $3.45, $3.16, but one particular day has a price of gas of $16. You know that's wrong, and that data line or that observation needs to be ejected, taken out of the model. Okay, so you have to look through all those data points and see if they're realistic. The most common way of doing that is to eliminate data points that are outside of 3 standard deviations. Okay, so you would get an average price of gas, you would get a standard deviation, you'd calculate 3 standard deviations above and below the mean, and any thing that lies outside of that range would be deleted. Okay. Also, this can only be used for data that is normally distributed. A lot of data is, but a lot of data isn't, right? To be normally distributed, it's got to have a mean, and the values need to fall equally on either side of that mean, right? It needs to have that familiar hump. You know, if you were to calculate the data, let's say you were to lay all the prices of gas out, you know, from $3 to an average of $3.5 all the way up to $4, right? Well, the average or the most frequent occurrence is going to be 3.5. However, we have occurrences of 325 and 320 and 315 and 310 and 305 and 3. And we also have, you know, a lot of occurrences of 365, etc. So if you were to plot your data, you would get that familiar bell curve look. That's normally distributed data. And remember in class recently, we looked at data. If you were looking at the number of children that women in Africa have, right? I don't really know what that is. Let's just guess the average woman in Africa has 4.3 children, right? If you were to find a standard deviation of, I don't know, even 6, right? You can't have a negative number of children, right? So you can kind of see that if you were to plot that, you couldn't have a standard deviation that is equally on both sides of the mean, right? So that data would not be normally distributed. The easiest way to test it is just to plot it and make a graph of it and see if it looks relatively like a hump that you're familiar with. Okay, I think that's enough, but you know, just go back through that, make sure your significance F is low enough before you go any further. Know that your R squared is only as good as you've got something to compare it to, right? If you're looking at 1R squared by itself, you don't really know if that's good, right? If I've been working on this model every week for the last year and you know my R squared is getting higher, that's a good thing, right? In that case, that 0.59 might be good. However, if you know I'm comparing it with something else, if I've got another model that gives me a 0.79, then this might not be a good R squared, right? So it's all relative. And okay, so that's something I would like you to be able to do, because from this point on you're going to look at regression outputs a lot, right? When you start your job, you may have to generate a lot of them, but ultimately it's important to know how to interpret them. Okay, all right, thank you.